Well, I wanted to thank the organizers and everybody who worked so hard for this conference to happen. I'm very grateful to be here and to have the opportunity to speak. So today I wanted to tell you two stories. The first is about a really nice connection between two combinatorial algebras. The face algebra, which comes from the world of hyperplane arrangements, and the descent algebra, which is a special subalgebra of the symmetric group algebra. And the second story is going to generalize and build upon this connection. In particular, the face algebra will carry actions of both the symmetric group and of the descent algebra, and I aim to tell you how these two actions interact. Okay, so I'm going to tell you these two stories. So let's start with the first one, explaining the connection between these two algebras. And to define the face algebra, I first need to explain the braid arrangement. And the braid arrangement is a popular example of a hyperplane arrangement. It lives in n-dimensional Euclidean space, and it consists of the hyperplanes xi equals xj for all pairs ij between 1 and n. And I've drawn out the example for n is 2 and n is 3 below. And as you can see by these red arrows, we often think about them in one dimension smaller by projecting or intersecting with some hyperplane orthogonal to the all ones vector. Okay, so the braid arrangement can be subdivided into smaller pieces called faces, and these are going to correspond with ordered set partitions of 1 through n, just by expressing orderings on blocks of equal coordinates. So for example, one face, this face here, will consist of all the points where their second coordinate is the largest, but first and third are equal. And there will be 13 total faces when n is 3, 1 zero-dimensional origin, 6 one-dimensional rays, and 6 two-dimensional chambers. Okay, so the faces are more than just a subdivision. Surprisingly, they carry an associative multiplication operator. And I think this is best described through example. So let's let F be this yellow ray here, and purple be this, or in G be this purple ray. The way you multiply F times G is you pick some starting point in F, any point is okay, and then take an epsilon step along a line from F to G. So when you do that, you're going to end up in some potentially new face. Here we end up in this two-dimensional chamber. So this chamber is F times G. Now note that this operation is not commutative. In particular, if we wanted to multiply G times F, I'd be starting on this purple ray, taking a step towards F, and I end up in this chamber instead. So it's not commutative, but something you can try to convince yourself of is that this center origin, this is going to be a two-sided identity. So because of that, the faces are going to form a monoid. And the symmetric group action will interact well with this monoid structure in that it acts by monoid automorphisms. Okay, so if you haven't seen this multiplication before, it might seem a little strange to do. So I wanted to give some context into why people study this. So more than the plain face monoid, what people really tend to study is the associated algebra, which is called the face algebra and written as CFN. And this just means all C-linear combinations of faces, and you extend multiplication linearly. So it's most popularly known for its connections with Markov chains and card shuffling. It turns out that you can model several popular Markov chains inside the face algebra and then use the combinatorics of the braid arrangement to get the eigenvalues. But more recently, it's been studied just as an interesting algebra in its own right. In particular, its representation theory is very nice and also governed by the combinatorics of the arrangement. And perhaps the reason that will be most useful for our talk is that it's highly connected to Solomon's descent algebra. which I'll now explain. Okay, so like the name suggests, the descent algebra has to do with descents of permutations. And we call a number I a descent of a permutation if the value of the permutation at I is greater than its value at I plus 1. So let's say we have this permutation here written out in one-line notation. 7 is greater than 5, so there's a descent at position 1. 5 is greater than 1, a descent at position 2, and so on. So the 4 descents are going to be 1, 2, 4, and 6. Now, what you can do when you have these descent sets is you can fix some subset and sum all the elements who have J as their descent set. And you get some element in your group algebra. But what's really surprising is that if you take the C-span of all these elements, they're going to be closed under multiplication. So they're going to form a subalgebra called Solomon's descent algebra, and we'll write it as sigma n. There should be an n right there. Okay, so I've kind of mentioned before that this is connected to the face algebra, and now I can tell you why. So this key connection is due to Bidiger, who proved in his PhD thesis that the descent algebra is anti-isomorphic to the invariant subalgebra of the face algebra. So I'm going to denote invariant subalgebra like this with a superscript Sn, and this just means all the elements of the face algebra who are fixed under the action. And this was a really nice and celebrated result because people had been studying the descent algebra for a while, but this gave it a new perspective, and it turned out to be a very useful perspective. And one example of how is that Saliola computed the quiver of the descent algebra using this embedding. So he had computed the quiver for the face algebra and kind of used this knowledge of it as living inside it to really figure that out. Okay, so that's kind of the first big idea. We have these two algebras, and they're connected by taking symmetric group invariants. So now I want to move to the more general story. And to do that, I'm going to say, like, what generalizes invariance? And one such option is these things called isotypic components. So just for this slide, let's zoom out to the more general setting of some finite group G acting on a finite dimensional algebra R. Under these conditions, R is a representation of G, and in particular, it's a semi-simple one. So we could fully decompose it into a direct sum of irreducible G representations. Now, that full decomposition is not going to be unique, but what is unique is the coarser decomposition you get by grouping the isomorphism, grouping the irreducibles of the same isomorphism type. And these are called isotypic components. So I'm going to think about this kind of more visually. Like from now on, all of my algebras are going to be these rectangles. And when I decompose them into their isotypic components, I'm going to be drawing them as rows. And so you'll have one row for every irreducible character of your group. And note that this bottom row, so when your character is the trivial character, is exactly the invariant subalgebra, which is why I say this is a special case. Okay, so in addition to each isotypic component being a G representation, it actually also carries the additional structure of being a module over the invariant subalgebra. So we have all these little extra actions to study. And these are typical things to study in classical invariant theory. Okay, so let's kind of go back to our situation. Our group was the symmetric group, and our algebra was the face algebra. So what do the isotypic components look like there? Well, I've told you about one of them. So Bidiger studied the invariant subalgebra, and that's the isotypic component for the trivial character. What I didn't tell you, but you can go read about it, is he also did a similar thing for the sign isotypic component. He studied the isotypic component for the sign character. He proved it's always one-dimensional, nilpotent subalgebra of the face algebra. And like we said on the previous slide, each of these components is a module over the invariant subalgebra. So in other words, because of Bidiger's anti-isomorphism, it's going to be a right module over the descent algebra. And this brings us to kind of the main question here, which is, how does each isotypic component look as a module over the descent algebra? And there's like a couple of motivations for this. One, it's kind of a natural extension of Bidiger's theorem from the perspective of invariant theory. But two, it provides new concrete representations of the descent algebra to study. Okay, so to answer this, I want to tell you a bit about the representation theory of the descent algebra first. Okay, so it was studied in depth, first by Garcia and Reutenauer, and then quickly generalized to other types by Bergeron, Howlett, and Taylor. And its simple modules are all one-dimensional, and they biject with our favorite combinatorial objects, the integer partitions of n. And this also means that the idempotents in a complete family of primitive orthogonal idempotents will also biject with partitions of n. But the descent algebra is also pretty rich. In particular, it's not a semi-simple algebra. So when you want to study its representations, you can't expect to fully decompose them into a direct sum of simples. You need some alternative way to understand them. And one other metric you could use are composition series. So let's say you hand me a descent algebra representation V, and I want to understand it. One way I could do this is by building a composition series of V. And even though that's not unique, what is unique is the number of times each simple shows up in that composition series. So this is getting covered a little bit, but it's the goal that we're going to do is count the composition multiplicity for every simple m lambda. Okay, so I'll start by giving you kind of a preliminary answer to the question. So we have these isotypic components. These are the rows in our rectangle. We want to understand them. One thing we can do is make our problem a little bit easier and break up that row into smaller pieces. And we'll do that by breaking it up into pieces that are also indexed by partitions of n, like everything in this project. So we won't really need them, but I think the dimensions are kind of nice, so I put them down as well. The dimensions are quite combinatorial and involve Koska number, standard Young tableau, and counting compositions that rearrange to a certain partition. So visually, all this proposition has done is this. I had my whole algebra here, which is the rectangle. Each row is a symmetric group isotypic component. And now I've just broken down each row into smaller boxes. And now I can just study each little box instead. But this leaves a lot to be desired, because all we really know are the dimensions of each box. But each box is a module of the descent algebra, and we want to understand the module structure. So this is not ideal. What we'd really like is if we could fill in what the composition factors are in each box. So if you want to think about this as more of a counting problem, something you can think about is, I want to know if you're given a partition nu, and if you're given two partitions, nu and mu, how many lambdas should I draw in the nu mu box? So for every box, how many lambdas should I draw? Now, fortunately, some of these numbers were already known. So the bottom row is essentially the descent algebra up to anti-isomorphism. And it turns out each box in the bottom row is something called a projective and decomposable module. So these numbers mean something. These numbers are the Cartan invariants of the descent algebra. And these were known in Garcia-Reutenauer's work. Similarly, the rightmost column is also known due to work of Uyemura Reis, kind of from the perspective more of shuffling. And I wish I had time to really go into depth with their answers because they're both very beautiful, but I'll just kind of flash them at you and say a little bit about it. And hopefully, if you're interested, you can read more. So the Cartan invariants of the descent algebra are exceptionally nice, I think. Here, this pink theorem is saying that if you're in the bottom row and you look in the box, the mu box, the number of lambdas you should draw, you just count the number of compositions rearranging to mu who have Linden type lambda. So I'm not telling you what Linden type is, but it has something to do with Linden words. And this is like I think this is a very nice result. In the rightmost column, it's a little trickier. So say we're in the rightmost column, but we're in row nu. The number of lambdas we should draw is the number of standard Young tableau multiplied by this inner product. So the inner product is between a Schur function and something called a higher Lie symmetric function. And you might wonder why this was considered kind of done, why are we okay with just leaving this inner product here? And that's because this is a long-standing open problem known as Thrall's problem to determine what these inner products are. And I think some of you heard about this last week in Leipzig. Okay, so my work aimed to unite these and extend these by telling you how to fill in the remaining boxes. And so we won't need to fully understand it, but just to kind of give you a picture of what it looks like. Say you're in row nu and column mu. The number of lambdas you can draw is given like this. So it starts out by looking like Uyemura Reis' theorem. There's an inner product, and here it's between a Schur function and some coefficient, some lambda mu coefficient of a generating function. And the generating function looks like this. And all I really want to point out is it involves Linden words, and it involves these higher Lie symmetric functions. So you can use this to recover both of the known cases. Okay, so in the last minute or so, I want to say just a little bit about the proof. It gets long, but there are parts that I think have very nice combinatorics, so I just wanted to say a bit. So I kind of started out with this problem, I wanted to understand for every box, I wanted to understand each box as a representation of the descent algebra. Kind of the first step, which was very key but not very hard, is to turn this into a problem about symmetric group representations instead. So it turns out to be, you can reduce this to understanding these double idempotent spaces, just using some standard finite dimensional algebra theory. And then even though this looks nice, these idempotents are quite tricky. And so if you really want to get your hands on the characters, you have to do something to them. And what was kind of key here is Franco Saliola's work on the quiver of the face algebra. And using his work, you can actually turn this into a question about poset topology. And basically, this turns out to be the representation of just intervals in the partition lattice induced up. And here, Sheila Sundaram has a lot of amazing work on the homology of the partition lattice, and you can apply this to kind of really get your hands on what those characters are. and turn it into symmetric functions. Okay, so that's all I wanted to say. If you want the details, you can go to the preprint. But thank you for listening.
Okay, thank you. Any questions?
So forgive me for asking, is there a Q analog question, but is there a natural grading on the representation that gives you some kind of way to take that number of standard Young tableau and split it up into finer pieces?
Like, you mean this number of standard Young tableau? Not that I know of. There is kind of a grading you could do for the last column. There might be actually in general, but it has more to do with the poset topology interpretation. For splitting up the standard Young tableau, what did you mean there?
Well, I want to get finer information out in some way because standard Young tableau have lots of nice statistics on them, and so maybe one of them somehow corresponds to a natural grading was my thoughts.
I see. Okay, cool. Thank you. Yeah, that's a great question.
Other great questions? Can you speak out loud?
This one? This one? Oh, yes. Okay, so this part's plethism, and then this part's like...
Could you repeat the question? Maybe.
Oh, the question was, what are these HWs? And so I guess these W's are words, so like W1, W2 through WN, where W1 through WN are just integers. So I'm thinking of HW as HW1 times HW2 times HW3, where H is the homogeneous symmetric functions. Yeah.
Also, do you know if there are any partitions that you could choose that actually you can evaluate this in a product?
Yeah, there are some special cases you can do, like,
Could you repeat the question?
Oh, sorry. Yeah, the question was like, can you sometimes like actually evaluate what this inner product is? Like, I think the one that's maybe easiest is like just for the sign isotypic component, you can explicitly evaluate, and it's always going to be either M22 or M22, or okay, it's the shape below the M will be the cycle type of the longest word in the symmetric group. And this actually works for other Coxeter types too. It's the simples are indexed by this analog of cycle type. And it's always this like longest word thing. Yeah, but not in general, and not that many special cases. Yeah.
Okay, so if you have more questions, please ask her after the talk. So let's thank Patty again.